Hello, everybody. Today's is our 12th lessons in the series Computational Materials and Molecular Design for Newbies. And today we have a guest speaker, our guest teacher, who is a professor at University North Carolina at Chapel Hill, right? Correctly?
Chapel Hill.
Chapel Hill.
Yep.
Dmitry Kireev is my old friend, and we worked together a long time ago in a place called Chernogolovka. So he left Russia, as I did, long time ago. Worked for how many years in France?
15 or 17, something like that.
Yeah. Il parle bien français, much better than I do. So, and how many years you are in the United States?
Well, since 2008, so it's almost 12 years, almost.
Yeah. So Dmitry is an expert in computational drug design, which is also part of the what is called computational materials design. And I believe today he will be talking about ligand docking and proteins. And he will be using our two free software. One is called UCSF-Chimera, and another one is called SwissDock. I will just for a short time, so that you can find this program, they both are free. So you can use them and learn them how to operate. So Dmitry would show you a couple of samples. So I'll just show you the website, the websites of both software, so that you can find it and download them. So this is a website of UCSF-Chimera. So if you do Google search, you just look, in order to come to the right place, you just search for UCSF-Chimera. So, and another software is called SwissDock. So, and Dmitry will tell you why he needs the both of them for the example. So, Dmitry, do you see the SwissDock right now?
Yes, I do.
So I showed both of them, all right? Okay, so so if you stop the screen and write down the address of both SwissDocs and UCSF-Chimera, so then you can easily find them either with these addresses or with just doing the Google search for these two software. So I'll do stop sharing and stop talking and so
right.
Welcome and thanks for joining us.
Thanks, Anatoly, for inviting me. So I'll share my desktop, and I guess you should now be seeing.
We'll see SwissDoc.
Right. So I'll just give a few words of introduction. I'm trying to make disappear that ugly menu, which prevents me from doing stuff. Maybe I'll need to hide. Yeah. Okay, so I'll give just a quick introduction into docking in general. Docking is an algorithm that searches and finds the way a small molecule ligand binds to a protein. And this is a central algorithm in multiple drug discovery tasks because, well, it's basically the one of the goals of drug discovery to find a molecule that could block or activate some protein target. And so for a typical docking exercise, we obviously need a 3D protein structure, then structure of a ligand or a database of ligands, because there is also a task which is called virtual screening, where docking is applied to thousands or even sometimes hundreds of thousands or millions of molecules in order to find the one that binds best to that protein, to the protein of interest. So SwissDock is one of the best. Well, at least it's a good docking algorithm, and it's freely available online. So you don't even need to download this software. You just need to open that site and start the process. There will be a couple things that we will need to do using another software called Chimera, as Anatoly already showed. So let's just go through the steps with SwissDock, and you will see what we need to start the docking. So first, well, sorry. Let's go to Submit Docking tab in SwissDock. You see it's now white, so it means that this tab is active. And the first thing the program invites you to do is to somehow define the target protein. So it can be a PDB code. So PDB, you see a page of a PDB. PDB means stands for Protein Data Bank, and it's a huge repository of all known 3D structures of biological molecules, proteins or RNAs, and it's a sort of
free, right? The access to the PDB bank is also free, right?
Yeah, absolutely. Yeah, and in this database, each molecule, each structure is defined by such a four-letter, four-digit code. Well, four letter, let's say, code, and so this SwissDock is asking for that PDB code to define the target. And we will use protein called MER kinase. And I picked this protein because it's a cancer target that my lab is working on. In fact, my lab contributes to drug discovery effort of anti-cancer agents. And one of the molecules that we designed, that we discovered, is currently in clinical trials. And so let's just pick that. We can copy it. And paste, sorry, I got the boring Zoom menu, which prevents me from doing that. Okay. So we just paste that, oops, code. No, it's not what I copied. Anyway, it's 4M3Q. So let's just type 4.
Oh, it's already remembered.
M3, yeah, 3Q. And search. So it says it found. So we add, we press the plus sign. So this will add the target. But then it's asking for our attention. In fact, there are two chains in the structure. So if we...
the dimer, right?
Right. Well, it's two... sorry, I'm... so if we check it here, 3D view in PDB, well, here it shows only one molecule, but well, anyway, there are two chains and we need to pick only one of them. So we pick the chain A and press select for docking. The next step is to pick a ligand that we are going to dock. And to choose a ligand, well, for our particular task, we will only pick one to make it quick. And also, I pick one that I know for sure is a ligand, is a binder for that protein. Otherwise, if you want to use your docking exercise, I mean, in the future for virtual screening, then a good resource is called zinc. So zinc is a free database of commercially available compounds that was also developed by University of California, San Francisco. And here you can find basically any kind of compounds, any kind of subsets. Like here, I've chosen to display all subsets that they have. There might be useful subsets like all FDA approved drugs, 1379. So for example, for COVID-19 screening, many computational groups were using this subset of approved drugs, because otherwise, if you want to develop a new drug for COVID, and you start from scratch, this would take many years. While if you manage to find some approved drug and find that it binds tightly to one of the COVID proteins, to one of the SARS-CoV-2 proteins, then this drug can go to clinical trials almost immediately. So lots of effort was in this direction. So anyway, like I said, we will not take any large subset, but we will use another free resource that is very useful, that is called PodChem. And PodChem, it's even a larger repository of basically all known chemical molecules. Over 100 million molecules. And we will find one molecule in particular that I helped to design, which is called UNC 2025. And like I said, we picked this particular one because I know for sure that it binds to the target. And so one convenient thing about this PodChem site, that for every compound that they have, you can download either 2D or 3D structure of that compound. So we will download a 3D conformer, 3D structure of this UNC 2025 compound and save it somewhere on my computer. So this will be downloads folder that I cleaned more or less before this lesson. So now we have that 3D structure of the ligand, but there is one thing. So we can see here in ligand selection that, sorry, things are changing, that it only takes, so I just selected this portion of text. So it needs a file with 3D ligand structure in mol2 format. And we have file in SDF format that we have just downloaded from PodChem. So we will use the Chimera software to convert the molecule from SDF to mol2 format. So we open Chimera, go to File menu, open. So we are in Downloads folder already, and we pick this UNC 2025 SDF, and we see that molecule that we have downloaded from PodChem. And now we go to File again, and we choose Save Mol2 in the menu. And we save it as a UNC 2025 mol2 file. So now we can go back to
so you actually used Chimera only to convert file, correct?
At this point, yes, but we will use Chimera once again soon. So now we can pick the ligand, sorry. Upload file, browse, and pick UNC 2025 mol2. Okay.
So first download protein and upload protein and then the ligand. So
right. And so you could see that we didn't even need to download the protein file because SwissDock just got it directly from the PDB database. So now we need to name the job. Well, let's name it MER. MERTK by the name of the protein. And well, it's optional. I can type my address, my email address. So it would send me an email when docking is started and when it's finished.
And also students now have your email and they can send you the questions.
Right. And that's basically it. We just press start docking.
Dmitry, can I ask a question? So how did ligand know the area which you need to bind? So the docking area has to be predefined somehow, or it's go around the whole protein area and try to find the place where to dock?
Right. Well, when you use a typical desktop software like Chimera or my favorite software is called Maestro Schrödinger. So in the more professional setting, in fact, the modeler is supposed to pick the site himself where the compound would bind. And there are several ways to do that. For example, if your crystal structure comes already with some ligand in it, it might be a natural cofactor if it's an enzyme. It can be some other co-crystallized ligand. So you can just pick that small molecule and it will use it to automatically define the binding site. Otherwise, you can tell the software which residues, which particular residues, as you think, determine the binding site. And sometimes if you don't have a clue where a molecule can bind, because some proteins naturally have pockets for binding small molecules like receptors or enzymes. Some don't. There might be just some signaling proteins which don't have natural pockets. So you can use another type of software which will search for any sort of cavities, small pockets in the protein which might be targets for docking. But as we see, SwissDock algorithm just think it's smart enough to to know what you need.
So basically,
And
download the protein from the database. It
right.
have information inside where is the docking area. So the Swiss
Right.
analyze the protein and define the docking area itself. Correct?
Automatically, yeah. And for the particular protein that we picked, it was easy because the protein came with some small molecule co-crystallized with it. So I'm sure there is a condition somewhere in that SwissDock algorithm with telling that if you have some co-crystallized small molecules, then automatically pick that region as a target for as a pocket for docking. So now the task is ongoing, but I have already prepared the results of that because I just did same thing yesterday. So when calculation is ready, in fact, the docking one molecule is fast, but SwissDock, I guess, is popular resource. So you may, I mean, just waiting the server time to submit the task might take some time. So we won't wait for that. But this is the way you obtain the results. You will receive an email saying that please follow that particular address for your results. And when we open that link, the results page looks like that. So it has its own built-in viewer to see. So these are poses that of several alternative placements of the ligand in the protein. And so here's where a chimera kicks in again. So in fact, we can see the results of the docking not only in this, I would say, quite poor online viewer, but we can also launch directly from this site UCSF-Chimera. So it will open Chimera with these results, which we can see in much better quality using the Chimera interface. So I now launched that, and now Chimera, I just confirm that I agree.
Now we see the black screen.
Right, well, it's just doing something. So here, now we have two tabs in Chimera. So one is where you can click on a particular structure. There are several clusters of structures. And then in another tab, you see how it looks like. This one doesn't look particularly well because it's not well buried in the surface. I remember that this cluster may be a little more convincing. Anyway, it's something you see here. It sits significantly much more much deeper in the pocket, and hence looks more convincing overall. So anyway, now I would say what you need is to figure out what you would do with this dock structure. I mean, usually it's being used to speak with the medicinal chemist and propose some modifications based on the structure to the chemist. So, I mean, the way the conclusions you draw from this kind of structures vary greatly from one project to another. In fact, the docking may be false, but sometimes you need to dock several compounds which have different activities, and from the way compounds with different activities are docked, you will see if structure-activity relationships follow the way structures sit in the receptor, and then it will help you maybe to provide some guidance to medicinal chemistry. Anyway, you will also need to better visualize specific interactions between the ligand and the receptor, hydrogen bonds, and so, but for that you would need to learn this Chimera software in more details. But as to the docking, it's basically all the steps we need, and I've also walked you through all resources that you might need. So it was online docking algorithm, online docking service, SwissDock. It was potential resource for chemical libraries called Zinc. It was another database of chemical compounds called PodChem. And finally, this free but quite nice modeling software called UCSF-Chimera. Yeah, and that's basically it for today.
Thank you so much. Can you stop sharing?
Yes.
Oh, thank you so much. There was quite a lot of information and quite a lot of sources. Very useful. Thank you so much for your lesson. So we'll hope to see you again sometimes in our series. Thank you. Bye-bye.
Thank you. Bye.